Okay, every developer knows that feeling, right? That little knot in your stomach when you have to change some old code. Well, today we're going to talk about 5 principles that can turn that fear into confidence. We'll use Python to see how these object-oriented ideas help you write code that's not just working, but is strong, flexible, and truly built to last.
You've probably seen code that looks a lot like this, right? I call it the God object, or the Swiss Army knife class. It tries to do everything. Connect to the database, send emails, compress files, you name it. But the problem is, when one class tries to do everything, it becomes a master of none. You touch one little thing, and the whole house of cards threatens to fall over. It's fragile, it's confusing, and honestly, it's a nightmare to work with.
There's actually a term for this in the software world, software rot. And it's the perfect name for it. It's like rust. It starts small, but over time it just spreads, making your code base brittle, risky to update, and eventually it becomes this tangled mess that nobody wants to go near. So, how do we fight back? How do we stop the rot and build software that can actually stand the test of time? Well, the answer lies in 5 incredibly powerful design principles. They were first introduced by the legendary Robert C. Martin, and later, a guy named Michael Feathers gave them the perfect acronym, SOLID.
So let's kick things off with the S in SOLID. This is the single responsibility principle. And the idea here is beautifully simple. A class should do one thing and do it well. It should have one and only one reason to change. Let's look at this file manager class. On the surface, it seems okay. It reads and writes files. But wait, it also handles compression and decompression. Now, think about this. Your boss comes to you and says, hey, we need to use a new compression library. So you have to go into this class and change it. Then, a week later, they say, we need to add logging whenever a file is written. You're back in the exact same class. It has 2 totally different reasons to change, and that's just asking for trouble.
So the solution is to just break it apart. We create 2 specialized classes. Now, our file manager is only worried about one thing, reading and writing files. That's its whole world. And the zip manager is completely dedicated to compression. Each class now has a single, clear purpose. They're focused, clean, and best of all, independent. And this one simple change gives you 3 huge wins. First, your testing becomes so much easier. You can test file I/O without ever thinking about compression. Second, you get lower coupling, meaning the file manager doesn't need to know or care about how zip manager works. And third, your codebase just becomes a whole lot easier to navigate. It's like having a well-organized toolbox instead of a junk drawer.
All right, next up, we have 2 principles that really go hand in hand. They're the key to building systems that can grow and evolve over time, without you having to constantly break open the stuff that already works. The O stands for the open/closed principle. Now, I know, this sounds like a total contradiction, right? Open but closed? But the idea is brilliant. Your code should be open for extension, meaning you can add new features, but closed for modification, so you don't have to change existing battle-tested code. This shape class is a perfect example of what not to do. You see that big if-elif chain? That is a massive red flag. Every single time we want to add a new shape, maybe a triangle, we have to crack open this class and add another elif line. We are constantly modifying a piece of code that was already working, and that's a risky game to play. A much, much better way to do this is with abstraction. We create an abstract shape class that acts like a blueprint. It basically says, hey, if you want to be a shape in my system, you must know how to calculate your own area. Then, when we want to add a square or a triangle, we just create a new class that follows that blueprint. We've extended what our system can do without ever touching the original code. That's the magic.
And that leads us perfectly to the L, the Liskov substitution principle. This is the safety check. It's the rule that makes sure our clever extensions don't end up causing chaos. Basically, it says that you should be able to swap in any subclass for its parent class, and the program should still work perfectly without any weird surprises.
And here's the classic example that trips everyone up. It makes sense to think a square is a type of rectangle, right? But look at the behavior. With a rectangle, you expect to be able to change the width, and the height stays the same. But a square can't do that. If you change its width, the height has to change too. This breaks the contract of the rectangle class. It's an unexpected side effect, and it's a subtle bug that can cause huge headaches later on. Okay, let's land this plane with our final 2 principles. These are all about how we connect the different pieces of our software together, making sure those connections are smart and flexible, not rigid and tangled. The I stands for the interface segregation principle. The main idea here is to avoid what we call fat interfaces. Put simply, don't force the class to take on methods it doesn't need. Keep your interfaces small and focused. Check out this poor old printer class. It's being forced to follow the rules of this big, bulky machine interface that says it has to be able to print, fax, and scan. But this old printer can only print. So now it has to implement these fax and scan methods that it can't actually use, probably by just raising an error. It's carrying around useless baggage, and that's a sure sign your interface is trying to do too much. The solution is simple. We segregate the interface. We break it down into smaller, role-based interfaces. We create one for things that are printable, another for things that are scannable, and so on. Now, our old printer can just inherit the one interface it actually needs, printable, while a fancy modern printer can inherit from both. It's so much cleaner.
And finally, we get to D, for the dependency inversion principle. This one sounds a little academic, but the idea is actually quite intuitive. Think of it like a wall outlet. Your high-level component, like a lamp, doesn't care about the complex wiring inside the wall. It just depends on the standard outlet, the abstraction. This means you can plug in any lamp you want. In this code, our front end is tightly coupled to the back end. It knows exactly what the back end is and even knows the specific method name, get_data_ from database. This is a problem. What happens when we want to get our data from a new web API instead of a database? Well, we have to go back and change the front-end code. They're stuck together. So the solution is to invert that dependency. We create an abstract data source interface. Now, the front end doesn't depend on a concrete database anymore. It depends on this abstraction. And this is a game changer. It means our data sources are now pluggable. We can plug in a database class or an API class or anything else, and the front end doesn't have to change one bit. It's blissfully unaware of the details.
So, we've walked through all 5 principles: the S, the O, the L, the I, and the D. But what's the big picture here? Why do these ideas, some of which are decades old, still matter so much for us as developers today? When you put them all together, these principles create code that is just better. It's more maintainable because it's easier to find things, it's more flexible because it can adapt to change, and it's way more testable because everything is nicely separated. In today's world of Agile and DevOps, where change is constant, building on a solid foundation isn't just a nice to have, it's absolutely essential for survival. But this brings up a really interesting question, especially now. We are moving into a world where AI tools can write a lot of our code for us. So if a machine is writing the code, do we even need to worry about design principles like these anymore? And the answer is a resounding yes. 1,000 times yes. It doesn't matter if the code was written by a person or a machine, a tangled mess is still a tangled mess. In fact, you could argue these principles are more important than ever. As AI handles more of the grunt work, our job shifts from being just coders to being software architects. And an architect's job is to understand the timeless principles of good design. Solid isn't just about writing code. It's about engineering systems that last.